Hello friends, today we take up next topic, dual nature of radiation and matter. First we take up dual nature of radiation. Wave possess dual nature, wave nature and particle nature. First promulgation in this regard was made by Einstein. He said that a wave behaves as a material particle. He used Planck's idea that a photon of light possess energy E equal to h nu. Mark it as equation 1. Further, he said that if it behaves as a material particle, it must have energy E equal to mc square. Mark it as equation number 2. Since left hand sides of equation 1 and 2 are same, therefore the right hand sides must be same. Therefore we write h nu is equal to mc square. The c square we split into c as is, or we can write this equation as h nu by c equal to mc. Mark it as equation number 3. Now because mc is equal to p, mass into velocity is momentum, and nu by c is equal to 1 by lambda. Therefore equation 3 can be expressed as h by lambda equal to p. Thus a wave of wavelength lambda behaves as a material particle having momentum p. Hence it possesses dual nature, wave nature as well as particle nature. Now evidences of particle nature. Two evidences are given for the particle nature of wave. One is photoelectric effect and other is Compton effect. Now in photoelectric effect, we have seen that when a photon of energy, photon of high frequency or a radiation of high frequency is made incident on a photosensitive metal surface, electrons are emitted out. Here is the photon and an incident on an electron is emitted out. It means a radiation interacts with particle. It is possible only when wave behaves as a material particle. Similarly, we have the second evidence as Compton effect. When X-ray photon of energy E equal to h nu or equal to hc by lambda is made incident on a material particle, this is photon and this is material particle, it gets scattered with energy lesser than the energy of incident radiation and making an angle theta with the axis of incident radiation, with the direction of incident radiation, and phi is the angle made by material particle with the direction of propagation of the photon. Now lambda minus lambda dash, the difference in wavelength of the incident and scattered photon is given by the expression h by m0c into 1 minus cos phi. Now after this, having the understanding of the evidences of particle nature of wave, we go to now dual nature of matter. Now we discuss about wave nature of particle. Previously we have discussed about particle nature of wave. Now we discuss wave nature of particle. Louis de Broglie in 1924 proposed that a beam of particle, each travelling with momentum p, manifests wave character with wavelength lambda is equal to h by p, where h is Planck's constant The de Broglie wave hypothesis attributed wave-like character to material particle. This material particle possessed two different velocities, the wave velocity and the particle velocity. Let us see how it has two different velocities. Now the two different velocities of material particle. The expression of de Broglie wavelength is lambda equal to h by p. It indicates that a material particle possesses two different velocities. One which refers to mechanical motion of the particle and is represented by v equal to c square by u, and the other which refers to propagation of the associated wave represented by u equal to c square by v, where c is velocity of light given by the expression under root u into v, wave velocity into particle velocity. So thus a material particle possesses two velocities, wave velocities and particle velocity. Particle velocity is given by the expression v is equal to c square by u, and wave velocity is given by the expression u equal to c square by v, and c, the velocity of light, is equal to under root of wave velocity into particle velocity. Now we go to de Broglie wavelength in terms of kinetic energy. Now de Broglie wavelength can also be expressed in terms of kinetic energy. How it is? Let us see. We start with point 3, de Broglie wavelength in terms of kinetic energy. De Broglie wavelength is given by the expression lambda is equal to h by p, but momentum p is equal to mv, and mv is equal to under root of twice m into kinetic energy. Thus p is equal to mv, and it can be expressed as under root of twice m into kinetic energy. Therefore de Broglie wavelength can be expressed as lambda is equal to h by under root of twice m into kinetic energy, where m is the mass of the particle. The fourth point, we calculate wavelength of an electron on the basis of de Broglie wave hypothesis. Now in that, an electron was accelerated through a potential difference of v volts in discharge tube, and let us see how we calculate. The wavelength of an electron on the basis of de Broglie wave hypothesis was determined by accelerating an electron through a potential difference of v volts. Now according to de Broglie wave hypothesis, de Broglie wavelength lambda is equal to h by p, and it can be expressed as h by root twice m into kinetic energy. If an electron is accelerated through a potential difference of v volts, then potential energy EV of the electron at cathode is equal to kinetic energy of the electron at anode. Therefore EV is equal to kinetic energy. Therefore EV is equal to kinetic energy. Here therefore we express lambda E is equal to h by root of twice m into EV. Lambda E is equal to h by root of twice m into EV, and we substitute the value of h, m mass of electron, E charge on an electron, and V potential difference. Then we arrive at the result that lambda E is equal to 12.27 into 10 raised to power minus 10 divided by under root V meters, or lambda E is equal to 12.27 divided by under root V angstrom, where V is potential difference through which electron is accelerated. Now we come to certain numerical problems to understand the concept. Question number 16, in continuation with assignment 11, we come at question number 16. An electron is accelerated through a potential difference of 54 volts. Calculate de Broglie wavelength of electron. And when you solve it, it would come out to be 1.67 angstrom. Question number 17. Calculate de Broglie wavelength of 3 kg object moving with velocity 2 meter per second. And it would be 1.1 into 10 raised to power minus 34 angstrom. Question number 18. An electron and a proton are possessing same amount of kinetic energy. Which of the two have greater de Broglie wavelength? Justify your answer. So electron will have greater de Broglie wavelength, and you have to justify by calculations. Similarly, question number 19, a proton and an electron have same de Broglie wavelength. Which of the two is moving fast? Here you have to calculate kinetic energy. So we will see that electron is moving fast. Question number 20. Neutrons in thermal equilibrium with matter at a temperature of T Kelvin are known to have an average kinetic energy of 3 by 2 kT. Compute the de Broglie wavelength associated with neutrons at 300 Kelvin. When you solve it, it will be equal to 3180 angstrom. So in place of kinetic energy, in the formula lambda is equal to h by under root of twice m into kinetic energy. In place of m you put the mass of neutron, and in place of kinetic energy you write 3 by 2 kT, and in place of T you write 300 Kelvin. So you will solve it and you will get that it comes out to be 3180. Now question number 21. Calculate the ratio of de Broglie wavelength associated with a deuteron moving with velocity 2v moving with velocity 2v and alpha particle moving with velocity v. So you will find that ratio is 1:1. Question number 22. The de Broglie wavelength associated with the proton and neutron are found to be equal. Which of the two has a higher value of kinetic energy? So you will find that proton will have the higher kinetic energy. So this is all about today's topic. Thank you so much. I hope you would have understood it clearly, and thank you for listening patiently. Thank you so much. God bless you.